Let's investigate something known as electromagnetic waves, and beyond that, talk about what the electromagnetic spectrum is. So let's take a minute and kind of go through an exercise here. Let's say that we have a freely moving positive charge over here, and additionally I've got a positive charge over here that's constrained to, we'll say, a conductor of some sort. It's stuck in this piece of metal. It can move through the metal, we'll say, but it's stuck to it. It can't go anywhere else in space. Well, initially, these charges repel each other, and if I move this first charge upward, what that's going to do is it's going to cause the other charge to move down, to try to get away from this positive charge. And if it moves back, well then the same thing's going to happen. It's going to go right back to the center. And similarly, if we move that first charge on the left down, well then on the right one is going to move up, and once again to try to get away from this charge. And if we go back to the center, there we go again. But does this happen instantaneously? And the answer is actually no. It takes time for the charge on the right to experience the force from the charge on the left. But why is that? Now I've gone ahead and drawn electric field lines around my left-hand positive charge. And let's say this positive charge on the right is like a test charge. It is so small that it doesn't really generate any electric field lines of its own. It's just going to follow the electric field from this left-hand positive charge. Initially, it's pushed away, but it can't go up and down in the piece of metal. But if we were to shift this charge upward all of a sudden, well, these electric field lines, they don't instantaneously change. The field around the charge changes much more quickly than the field further away. You can kind of see this ripple effect happening, where this field that was away from the charge is still in the original position, and this field right next to it is now moved to its now current position. And as time moves on, this ripple is going to spread out through the line until eventually it makes it over here and causes this charge to move down. I want to be very, very clear. This is happening extremely, extremely quickly, nearly instantaneous, but not quite instantaneous. Now let's go back a step and simplify that picture a little bit, because that drawing was a little bit complicated. And let's instead focus on, as that ripple of the electric field happens in space, let's only focus on the vertical portion of it, particularly because this test charge can only move vertically. It doesn't really care about the horizontal portion of the electric field that much. And so as I move this up, the electric field is going to ripple downward because charges would be pushed down away from it. But the thing is, though, I'm not going to leave this charge here. I'm now going to start oscillating it back and forth. So as it comes back down, well then this ripple has now kind of ended. It goes back to its original state. And now I'm going to oscillate it downward, and as I do that, I've created an electric field upward, and I'm going to do that one again, and I'm going to keep on going through time. So let's look at that picture again, but this time let it play out a little more quickly. So as a charge oscillates up and down, it creates this wave-like pattern in the electric field. And in fact, it's a wave that is propagating to the right at some speed v. And keep in mind, the speed is incredibly, incredibly fast because the charge on the right experiences that field change almost instantaneously. But let's pause there for just a second. We have created a changing electric field here by having this charge oscillate up and down. It's perpetually changing because the charge is continually slowing down, speeding up, or reversing direction as it goes through essentially simple harmonic motion or oscillating motion. But the thing is, though, if we have a changing electric field, well, that is going to be creating a changing current because this charge is moving back and forth, and so it's going to continually have different values in different directions. But if we have a changing current, that means we are creating a changing magnetic field because magnetic fields depend on electric currents or moving electric charges. But if I have a changing magnetic field, what we've learned through electromagnetic induction, the changing magnetic fields through changing magnetic fluxes create currents. And those currents, if the magnetic field is continually changing, that current is going to be continually changing because the electric field is continually changing. And what we're seeing here is we're getting this cycle happening of a changing electric field and a changing magnetic field inducing each other simultaneously and going back and forth, oscillating in and out. And this was noticed first by a Scottish physicist known as James Clerk Maxwell, arguably one of the top physicists of all time, with maybe the only exceptions being Newton and Einstein. And he noticed this and then took it a step further in order to mathematically analyze it. So let's go back to our picture. We have this wave of a changing electric field through space, propagating at some incredibly fast speed v. But if we have this changing electric field, we also have this changing magnetic field b that is also going through space with it. So the electric field lines here are the orange lines, the light blue lines are the magnetic field lines, and these fields, remember, are perpendicular to each other, and they're also perpendicular to the way this is traveling. So as the electric field points down, the magnetic field points kind of into the screen, and as the electric field points up, the magnetic field points out of the screen. This is about the best I could draw that with a 3D representation. But what we have here is a continuously moving disturbance in the electromagnetic field, or this combined electric and magnetic field, that's transferring energy and momentum from one electric charge to another electric charge. And this is, in fact, an electromagnetic wave, and that is what James Clerk Maxwell derived, was that as this occurs, an electromagnetic wave will occur. And when he did his calculations, he noticed something very bizarre, which was that the speed that these go through space was actually 3 times 10 to the 8th meters per second, or about 300 million meters per second, which was similar to something he'd seen before, because this wasn't about in the 1870s, and over the course of the past couple decades, people have been doing more and more accurate measurements of the speed of light. And that speed came out to be pretty close to 3 times 10 to the 8th meters per second. And that is when the light bulb clicked on for James Clerk Maxwell, because what he realized was this electromagnetic wave was actually what light waves are composed out of. Light is an electromagnetic wave. So electromagnetic waves are often called light waves. They are really one and the same. And they are self-sustaining, continuously moving oscillations in this joined electric and magnetic field created by some oscillating charge. You oscillate a charge up and down, in and out, right and left, whatever. That creates an oscillation in the electric field and simultaneously an oscillation in the magnetic field that are perpendicular to each other, and they propagate out through space continually, inducing each other. Now, this electromagnetic wave is a transverse wave. This is a 3-dimensional wave. And what we mean by that is that the electric field oscillates in one dimension, which in this case is pretty much up and down. The magnetic field oscillates perpendicular to that, which in this case is in and out of the screen. And the wave itself actually moves in the 3rd dimension. So the wave is moving, in this case, to the right, as both of these fields are oscillating. Now, additionally, and this is very surprising, that electromagnetic waves can exist independently of matter. And this is completely different from the mechanical waves like sound waves. But electromagnetic waves, because they're self-sustaining and they are literally just excitations of the electric and magnetic field, don't require anything else but the field. So they can exist in a perfect vacuum. And then lastly, and in this vacuum, they always travel at a very specific velocity. And that velocity we label as c, which is 3 times 10 to the 8th meters per second, or specifically known as the speed of light in a vacuum. So what are some properties of these electromagnetic or EM waves, aka light waves? Well, first, their speed in a vacuum is always c is equal to 3 times 10 to the 8th meters per second. You want to write that down? You might as well go ahead and memorize it. This number is going to come up a lot. And remember, this is constant. Well, what's another property we know of waves? Well, we know that there's something called the amplitude. For this, it's really the maximum strength of the electric field and the magnetic field as this wave moves through space. Now, we typically don't focus too much on the amplitude, particularly because there's 2 different amplitudes, one's for the electric field, one's for the magnetic field, but it's important to realize that they are very closely related to the intensity or the brightness of a light wave. If you have a very, very bright light wave, that means its electric field has a much bigger amplitude than one that is dim. Another property we have is a property of frequency. Now this determines the type of light we're analyzing. And we're going to learn real soon there are multiple types, so we'll get to that more in a second. Additionally, waves have this property known as wavelength. And we used to calculate for mechanical waves, we use this equation of lambda is equal to v over f. That if the wave is moving faster, it has a bigger wavelength. If it has a bigger frequency, it has a smaller wavelength. And this relationship still works. But the thing is, though, is that we no longer have v, because remember, the light waves in a vacuum only travel at c. So I'm going to rearrange this and just say c is equal to f lambda, where c is the speed of light, which usually we will talk about the speed of light in a vacuum, so that's 3 times 10 to the 8th meters per second. F is the frequency of the light wave in hertz, and the wavelength is in meters. Remember, this has to be very clearly in hertz and meters specifically. But the thing is, though, is if we look at this, we have one number times another number is going to equal a constant. And that tells us that for every particular frequency, well, it's going to have its own specific wavelength, because that frequency times the wavelength must equal this constant number. There's no other options. And so while the frequency of light is really what determines the type of light that it is, the wavelength is also closely related to this, because frequency and wavelength go hand in hand. They each have their own unique partner when it comes to light. Now, just a minute ago, I talked about that there were different types of light waves that depend on frequency and related to that wavelength. And this is known as the electromagnetic spectrum. It's this broad range that we can put all the different types of light into based on their specific frequencies and wavelengths. And it's very, very crucial that we at least get the order of these, and additionally that we figure out, okay, which ones have longer wavelengths, which ones have shorter wavelengths, which ones have high frequencies, which ones have short frequencies. So I would go ahead and take your notes and probably rotate them, do like a separate page and rotate it horizontally so you can put this in your notes, and we're going to add a lot of details here. So looking at this very long spectrum, we're going to have on the left-hand side long wavelength, and that is inversely related to frequency. So these are going to be low frequency waves that take a long time to oscillate. And on the other end, on the right-hand side, we're going to have short wavelength and high frequency. So these waves oscillate very, very quickly. And remember that all these waves are created by charges. And we're also going to focus on, well, what type of charges are creating these types of waves. And let's start with the one that we are most familiar with, because it is what we think of when we hear the word light. And in fact, many people would say it's really the only word you should use light for, and that is light in the visible spectrum, or visible light. And that ranges from wavelengths that go from 380 nanometers on the short end to 750 nanometers on the long end. Remember, a nanometer is times 10 to the minus 9 meters. And we're going to see nanometers a lot, so we need to remember that. And these light waves, well, we usually characterize them by their color, when we can physically see them. So on the short end, we have violet. On the long end, we have red, and going from long to short, we have Roy G. Biv, which you're probably familiar with, which is red, orange, yellow, green, blue, violet. And it's important to know the order of these and to know which ones are longer wavelength and which ones are shorter wavelength. So longer wavelength, red, shorter wavelength, violet. Now these are typically produced by oscillating electrons and atoms, and we're going to learn way more about that later on down the line. And the reason why we consider these special, even though this is an incredibly tiny part of the electromagnetic spectrum, it is less than 1% of the entire spectrum, but it is the part that our eyes, aka human eyes, have evolved to perceive. So we give it a lot of extra weight because really, until we realized that there were other types of electromagnetic waves, this is all we thought of when we thought of light. When we realized that this could encompass many other types of oscillations, this spectrum broadened out almost immediately. Alright, so let's go and start going to the long wavelength, low frequency end, and let's start off with the first one beneath visible light, which is infrared or IR radiation. Now these have wavelengths anywhere from the nanometer range to the millimeter range, so times 10 to the minus 9 meters to times 10 to the minus 3. And these are typically produced by oscillations not of electrons but of entire atoms and molecules. And that makes sense because we think of infrared radiation as being thermal radiation. When our molecules vibrate, they emit infrared radiation, which is why you can see them with like night vision goggles or heat vision goggles. You are picking up those waves. Alright, the next longest wavelength are microwaves. And microwaves have wavelengths that can go anywhere from millimeters to entire meters. And these are typically produced by electrons that are moving up and down antenna. Now these are specifically man-made microwaves. And we use them for all sorts of wireless signals. Cell phones, Wi-Fi, GPS, TV signals through the air. All of these are pretty much ubiquitously microwave signals. The last one we have on the long wavelength end of the spectrum is the longest wavelengths, which are radio waves. And these have wavelengths going from meters to entire kilometers, if not even longer than that. And these are typically also produced by, when they're man-made, electrons going up and down an antenna, and we use these for radio signals or things like radar. So this is our long end of the spectrum. Now let's go to the short wavelength, high frequency end of the spectrum. So right above visible light, we have ultraviolet or UV rays, which are typically in the nanometer region. And these are also produced by oscillations of electrons. They're just higher energy oscillations. Above this level, we have X-rays, which go anywhere from the nanometer range to the picometer range. That's times 10 to the minus 9 meters to times 10 to the minus 12 meters. Super, super, super tiny. And these are also produced by electrons typically. Once again, very high energy oscillations. And the highest frequency, or the shortest wavelength of light, are what are known as gamma rays, which are pretty much exclusively in the picometer or shorter regimes. That's times 10 to the minus 12. And these are produced by oscillations, not of electrons, but literally by oscillations inside the nuclei of atoms. But one thing I want to notice here is you'll notice there's a lot of medical stuff on this, and there's disinfection here. And the reason why is that pretty much this entire region above visible light, going all the way from about partway through UV, not all UV, but partway, including all X-rays and gamma rays, are what are known as ionizing radiation. And by ionizing, we really means that they're dangerous, that these can hurt you because they can actually destroy the DNA inside cells and create mutations and cancers of their own. And we will talk more about that later. So what are our main takeaways on this first lesson of light and optics, in which we talked about EM waves, or electromagnetic waves, and the electromagnetic spectrum? Well, first, can we explain how electromagnetic waves are generated with oscillating charges, and describe how they propagate through space, with the electric and magnetic fields being perpendicular to each other and oscillating, and also both perpendicular to the direction the wave is traveling. And keeping in mind that all of these electromagnetic waves are literally light waves. That is what light is. Can we identify or calculate the properties of these EM waves, such as the speed, c equals 3 times 10 to the 8th meters per second, the frequency of the wavelength, things of that nature? And can we distinguish the segments of the EM spectrum? And particularly, can we rank them from low frequency to high frequency, or low wavelength to high wavelength? And additionally, can we also do that with the colors in the visible spectrum, making sure we can also do low frequency to high frequency, low wavelength to high wavelength in that visible spectrum too?